Hi, in this lecture, the second part of the topics on the field effect transistor is introduced. By this slide, we will try to understand and become familiar with the DC analysis and design techniques of MOSFET circuits. An example of common source circuits is illustrated in the slide. The source terminal is at ground potential and is common to the input and output portions. The coupling capacitor behaves like an open circuit to DC, but it allows the signal voltage to be coupled to the gate of the MOSFET. The DC equivalent circuit is shown in the slide. Since the gate current into the transistor is zero, the voltage at the gate is given by a voltage divider. Assuming that the gate to source voltage is greater than the threshold, the transistor is biased in the saturation region and the drain current is introduced. Then the drain to source voltage is calculated. Finally, the power dissipated in the transistor is given. In the example, based on the given parameters and assuming the transistor is biased in the saturation region, the drain current, drain to source voltage, and power should be found. By employing the expressions we have just derived, under the saturation region assumption, the drain current, drain to source voltage, and power dissipated in the transistor can be easily calculated. A common source circuit with a PMOS device is illustrated in the slide. Similar to the circuit with the NMOS device, the gate voltage, the source to gate voltage, for the saturation region, the drain current, and the source to drain voltage can be introduced. In the example, for the given circuit, the drain current and the source to drain voltage need to be calculated. Let us first calculate the unknown parameters by assuming that the transistor is in the saturation region. By simply substituting the given parameters, the gate voltage and the source to gate voltage are found. Then the saturation level of the source to drain voltage is given. Based on the saturation assumption, the drain current is also calculated. Finally, the source to drain voltage is given. However, this also reveals that the transistor is in the non-saturation region rather than the saturation, since the calculated source to drain voltage is less than its saturation level. Since the transistor is in the non-saturation region, the drain current and then the source to drain voltage should be re-evaluated. By combining these two equations, the drain current is found. Then the source to drain voltage is given and this justifies the non-saturation region. In the example, for the given parameters, two resistor values denoted by RD and RS should be found. Note that since the DC analysis produces the quiescent values of the drain voltage and the drain to source voltage, they are usually indicated by IDQ and VDSQ. By assuming that the transistor is in the saturation region, the gate to source voltage is presented. Since no current flows in the gate terminal, the gate potential is zero. Then the voltage at the source terminal can be calculated. The source resistor is found. The voltage at the drain terminal is also given. Similarly, the drain resistor is introduced. Finally, the saturation region of the transistor can be justified. In the second design example, the parameters are given like that. Here, the value of the larger bias resistor is given as 200 kΩ, and it may be either R1 or R2. By considering the saturation region of the transistor, the source-to-gate voltage is given. By using the source-to-gate voltage, the saturation region is verified. Furthermore, the gate voltage can be calculated. Since the gate voltage is found to be positive and no current flows in the gate terminal, the larger resistor is R2 and R1 is calculated as 157 kΩ. The source resistor is easily given. The voltage at the drain terminal can be also found. Finally, the drain resistor is introduced. For the MOSFET circuits, the transition point is the boundary between the saturation and non-saturation regions, and it is defined as the point where the drain to source voltage is equal to its saturation level. Let us evaluate the transition point of the given circuit. We can express the saturation level of the drain to source voltage and the drain current. Then, by combining these two equations, the transition point of the transistor and the corresponding drain current can be calculated. Finally, based on the calculated gate to source voltage, the modes of the operations are clarified. By this slide, we will focus on some additional MOSFET configurations. MOSFET integrated circuit amplifiers are generally biased with constant current sources. Biasing with current source tends to stabilize circuits against variations in device or circuit parameters. Let us design a MOSFET circuit biased with a constant current source. For this circuit, due to the independent current source, the drain current will be equal to I sub Q. By assuming the transistor is biased in the saturation region, the gate-to-source voltage can be calculated. Since the gate voltage is zero, the source voltage is found easily. Then, based on the given values of the drain voltage and the current, the unknown resistor value is presented. Furthermore, the drain-to-source voltage is introduced and the saturation region is verified. The given transistor with this connection is called an enhancement-load device. Due to such a connection, the drain and the gate voltages are equal to each other, and they are always greater than the saturation drain voltage. Then this implies that the transistor is always biased in the saturation region. The current voltage characteristic is given here. As you realize, it behaves like a nonlinear resistor. If an enhancement load device is connected with another MOSFET, the circuit can be used as an amplifier or an inverter in a digital logic circuit. The load device is always biased in the saturation region. The driver transistor can be biased in either the saturation or non-saturation region. Assume that the parameters for the load transistor and driver transistor are given. The output voltage needs to be calculated for the two different values of the input voltage. Let us first solve the example for the input voltage Vi equals 5 volts. Assume that the driver transistor is biased in the non-saturation region, since the drain to source voltage will be small. Furthermore, the drain currents in the load and the driver devices are equal. Then, by following the sum equal voltage pairs, the output voltage is found. This result also justifies that the driver transistor is biased in the non-saturation region. Finally, the current is given. In the second part of the example, the input voltage Vi is set to be 1.5 volts. In this case, since the input voltage is relatively small, the driver transistor is assumed to be biased in the saturation region. Again, the drain current in the load device is equal to the drain current in the driver device. Then, by following the preceding equal voltage pairs, the output voltage is found. This result also verifies that the driver transistor is biased in the saturation region. Finally, the current is given. By this slide, we start discussing some basic MOSFET applications. The first application is the NMOS inverter. An NMOS inverter or switch is illustrated in the slide. In this circuit, the input voltage equals to the gate voltage, and the output voltage is the drain voltage. The transistor switch provides an advantage over mechanical switches in both speed and reliability. The transistor switch is also called an inverter. When the input voltage is less than the threshold, no current flows, and the transistor is off. As soon as the input exceeds the threshold, the transistor is on and initially biased in the saturation region. As the input increases, the drain voltage decreases due to the voltage drop on the resistor, and the transistor is biased in the non-saturation region. For this region, the expressions for the current and the output voltage are given. In the example, we need to design the size of a power MOSFET for a particular switch application. The load in the inverter circuit is assumed to require a current of 0.5 ampere when turned on. The effective load resistance varies between 8 and 10 ohm, depending on temperature and other variables. A 10 volts power supply is available. The process conduction parameter and the threshold are given. One solution is to bias the transistor in the saturation region so that the current is constant, independent of the load resistance. Since the load resistor changes from 8 to 10 ohm, the minimum drain voltage is found as 5 volts. The gate voltage level is selected to keep the transistor in the saturation region. Finally, the transistor width to length ratio is calculated. The next MOSFET application is a 2-input NMOS no logic gate, shown in the slide. Its operation is introduced in the table. When at least one of the transistors becomes on, a current flows in the circuit, and due to the voltage drop on the resistor, the output becomes low. However, when both of the transistors are off, no current flows, and the output is high. In the example, we need to calculate the resistor current and the output voltage for various input conditions introduced in the slide. When both of the inputs are 0, no current flows, and the output is equal to 5 volts. When one of the inputs is high, a current flows where the transistor is on. When both of the inputs are high, a current flows in both of the branches. In this case, the resistor current is the sum of the drain currents. Here it is important to note that the transistors are biased in the non-saturation region due to the voltage drop on the resistor and the small drain voltage levels. This is the last slide of this part.